In this video, we will investigate a few more examples involving the mean value theorem. So once again, for the given function, let's verify the hypotheses are satisfied and find all numbers C satisfying the conclusion. So recall what the hypotheses are. We need the function f to be continuous on the closed interval and differentiable on the associated open interval. So for the function that we are dealing with, x over x plus 2, it is going to be continuous and differentiable wherever it is defined because it is a rational function. So this is continuous and differentiable as long as the bottom is not 0. And x equals minus 2 is not in our interval. So if we make the restriction down to our interval, our function is certainly continuous on the closed interval from 1 to 4 and differentiable on the open interval from 1 to 4. So check. The hypotheses of the mean value theorem are satisfied. What we would now like to do is find any values of C satisfying the conclusion. So we want to find any value C where C is inside this interval from 1 to 4, and the derivative at C is equal to f of 4 minus f of 1 over 4 minus 1. And if we go ahead and simplify here, f of 4 is going to be the number, 4 6, so 2/3, minus f of 1, which is 1/3, all over 3, which is 1/9. So we need to determine what is f prime so that we have an equation to solve for C. So using the quotient rule, we have low d high minus high d low all over that bottom squared. The top is x plus 2 minus x, so just a 2 over x plus 2 quantity squared. So f prime of C is going to be 2 over c plus 2 quantity squared. And what we now need to do is solve for C. So to solve for C, we can multiply both sides by 9 and multiply both sides by c plus 2 squared. And this is going to boil down to being a quadratic type equation. And to solve for it, let's just go ahead and take the square root of both sides. So we'll say c plus 2 is equal to plus or minus the square root of 18, so that c is equal to minus 2 plus or minus the square root of 18. And of these two possible values, we know at least one of them is guaranteed to be in our interval, but let's see what they would be. So we have C1 maybe corresponding to the minus, and then we have C2 corresponding to the positive. Well, C1 is a negative number, so I'm going to cross that off and say not in the interval. So what that means is the other number has to be in the interval because we're guaranteed such a number exists. And if we plug this into a calculator, it's approximately 2.24. So we see, yeah, this is in the interval from 1 to 4. So another similar type of problem. So let's go ahead and verify that the hypotheses are satisfied. So f of x equals x cubed minus x is a polynomial and hence continuous and differentiable everywhere, which means that it's certainly continuous on 0, 2 and differentiable on the open interval from 0 to 2. So the hypotheses of the mean value theorem are satisfied. So can we find a value of C in the interval from 0 to 2 with f prime of C equals f of 2 minus f of 0 over 2 minus 0. So f of 2 is 6, f of 0 is 0, and 6 over 2 is 3. So we need to differentiate f prime x is 3x squared minus 1. And we want to know when will f prime of c be equal to 3. So that would be when is 3c squared minus 1 equal to c. And here we need to solve for that c value. So 3c squared is equal to 4. C squared is equal to 4/3. So c is equal to plus or minus the square root of 4/3. But of course, both of these values for c, the plus and the minus, will not work here because we need to be in the interval from 0 to 2. So only the positive value will work. So the solution here would be c equals the positive square root of 4/3. So 2 over the square root of 3. So that's the only value of c in the interval from 0 to 2. So these last few examples are all very computational in nature. Let's look at one more problem dealing with the mean value theorem that has more of a theoretical feel to it. So suppose that we are given that the function value f of 0 equals 3, and the first derivative of our function f is always less than or equal to 5 for all values of x. We want to use the mean value theorem to determine how large f of 2 can be. Now, luckily we're told to use the mean value theorem here, but it's not obvious how to proceed. In order to use the mean value theorem, we need a function. Okay, it's kind of just this arbitrary f, and we need an interval to apply it on. So what interval is it given to us? So apply the mean value theorem on which interval? Well, the interval is in terms of inputs, and I see an input of 0 that we know something about, and an input of 2 we would like to find something about. So let's go ahead and apply it on this interval from 0 to 2. And that is the key observation. So in order to apply the mean value theorem, we have to think about the hypotheses being satisfied. So we are told that f prime of x is less than or equal to 5 for all values of x. And what that means is that our function f has to be differentiable and continuous everywhere. So that means f is continuous and differentiable everywhere. Right? Because if it was not continuous and differentiable everywhere, we couldn't say that it's always less than or equal to 5. So specifically in terms of our problem, we can note that f is continuous on 0 to 2 closed, and f is differentiable on 0 to 2 open. So this tells us that we can apply the mean value theorem. So by the mean value theorem, and oftentimes I will just abbreviate MVT to stand for the mean value theorem, there is a c in 0, 2 with f prime of c equals f of 2 minus f of 0 over 2 minus 0. And the question is, what does this really tell us? We want to know something about f of 2, and we know what f of 0 is. So f of 0 is 3. So we can simplify this equation a bit, and we can say what? F of 2 is going to be equal to multiply both sides by 2 and add 3 to both sides. So we've just isolated that f of 2. We also know something about f prime of x. F prime of x is always less than or equal to 5. So this is less than or equal to 2 times 5 plus 3, which equals 13. So it didn't appear that we would know enough about the function to determine how large this value can be, but note that we've really done it. How large can it be? F of 2 is always less than or equal to 13. So the largest f of 2 can be is 13. And once again, just to recap, maybe the most difficult part of this problem was determining the interval on which to apply the mean value theorem. And the interval is in terms of inputs, so we just went back and thought about what inputs do we see in that problem statement.